Let's get started. Again, my name is Ryan Clementson. I'm one of the business development managers here at Tolomatic, and I will be your presenter today for this installment of ToloTalks, where we will be discussing converting of hydraulics over to electric actuators. Thank you all again for joining, and hope you enjoy the material today. What we're going to cover today, just do a quick kind of an interesting brief history and overview on the hydraulic cylinder market. We are going to talk a little bit about challenges and issues with hydraulics, including some of the total cost of ownership aspects that people sometimes overlook. We'll cover some application examples and successes that Tolomatic has had, and we're continuing to see more and more of these on a weekly, monthly, yearly basis. I want to talk a little bit about sizing electric actuators to replace hydraulic cylinders and some of the tips that we've learned and seen from doing these conversions, and pass along those tips for you. And also just kind of at the end here, talk a little bit about some of the resources that you can use and everybody just in the marketplace can use for helping to do these conversions. As many or most or all of you know, hydraulics have been around for a long, long time, somewhere, to the best of our understanding, somewhere between the 1600s and early 1700s. So it's been around for a few years. The hydraulic cylinder market in North America in and of itself is about a $3.8 billion or $4 billion market, and that does include the mobile hydraulics market. So it's a big industry. And, you know, there's a lot of industrial grade cylinders. When you take a look at industrial hydraulics, there's anything from a 1 to an 8-inch bore, some even bigger. It's pretty common to see pressure ranges kind of in that 2200, 2000, 2500 psi range, which is anywhere from 1,700 pounds to about 110,000 pounds or 55 tons of force. And people use hydraulics. They're simple. It's pretty easy to understand. Generally, simple hydraulic circuits are pretty simple to deploy. They're cost effective, especially in single axis applications. And hydraulic cylinders, because you can go even up to like 5,000, 6,000 pounds of force, the amount of power that you get out of a very, very small area is very, very high. So they've got what I call a good power density. And how do we compare from a Tolomatic standpoint to the hydraulic ranges that we're talking about? Is we kind of hit that 1 to 5 inch bore equivalent of hydraulic cylinders, and that gets us up to about 50,000 pounds of force, or anything underneath that. A lot of you know that have worked with hydraulics or been around them. There's some issues and challenges. They're very, very reliable overall, and the hydraulics aren't going away. But when you start taking a look at how they impact the manufacturing environment, they do provide a safety hazard where it's not a matter of if, but when hydraulic hoses are going to leak or break. To that effect, when you have an issue like that, you're going to see parts being scrapped out. You're going to have lost productivity time. You've got a lot of maintenance that you've got to be doing. Power units, depending on where they're located, they can be very, very noisy. They're not easy to change over, so you can even have long lead time or long changeover times for machines. And I suggest that you guys all take a look at the comment up here that profits, unnecessary energy consumption. I mean, there's lots of reasons why people are looking to replace hydraulics and go to something a little bit more efficient and not feel like you're pushing a ball uphill in some of these instances. And a lot of times, people that have been using hydraulics for a long time, they kind of lose sight of the maintenance cost, the part scrap rate, and lost productivity. And you kind of think about this from an iceberg principle, where oftentimes they'll take a look at the overall cost of a hydraulic system and say, yeah, it's really low cost by comparison to a big, electric actuator, but they're not looking at what's under the surface, and that's, the installation cost, the operating cost, disposal fees. If it's an outdoor application, you've got environmental costs. So there's a lot of stuff that goes into operating a hydraulic system that we kind of bundle into that total cost of ownership or soft costs outside of the purchase price. And so it's always worth asking the question, are you considering that in any type of engineering exercise, sizing exercise, purchasing exercise to truly compare an electric system to a hydraulic system. And so from that, we'll talk just about 4 points in the total cost of ownership spectrum. The process control, the reliability, the efficiency, and risk mitigation is certainly something too that we want to be aware of. And so from a process control standpoint, a lot of you do know and understand the benefits of going to motion control. I mean, they're programmable, they're flexible, you've got speed and force. You can get there with servo hydraulics, but there's a lot of complexity with using servo hydraulics. The electric actuators, as we talked about over the course of some of these other sessions here in the last few weeks, they're very, very consistent. It minimizes variation from part to part because of repeatability inconsistencies, especially as you get seals to wear or pumps to wear out. And more in a manufacturing environment, people are looking to get data. It's all about big data, right? And so, are you looking at how much force you're getting, especially in in a pressing application where you're able to get that out of the drive for current? Are you getting position feedback? And if so, how accurate is it in a hydraulic system? Well, you can get that out of a servo system. And flexibility, especially in North America, is very, very important. And so, and no doubt throughout the rest of the world too. People want to get more flexibility out of a single build or a single machine. And so minimizing the amount of time it takes to change to a different part or to adjust to a different setup, that's all very, very important in today's manufacturing environment. People want their machines to run. They don't like it when they're not running. So reliability is certainly something people are paying attention to more. When you take a look at your footprint, I talked about the benefits of a power dense hydraulic cylinder, but at the same token, when you take a look at the total footprint of a motion or an axis of motion, on the right here, we've got power units and cylinders and tank heaters, accumulators, heat exchangers, things like that for very, very, very aggressive applications. Well, with an electric actuator, you've got an actuator, a motor, and a drive that goes into some kind of an electrical panel. So your footprint overall is actually pretty small. It also minimizes the part count, things that could potentially fail, and it can even, in many cases, simplify your machine build. And kind of switching back over to the reliability piece, a lot of these actuators, you can get away with never having to lubricate them or never having to really do any maintenance to them. So now you're reducing your labor cost to keep the machine running. And with that level of reliability, you're eliminating that risk of unplanned downtime. The other side of the reliability piece is electric actuators are very, very consistent. They're very, very repeatable, to the point where now a lot of times, or you're seeing people are doing these L10 life calculations and having a really good understanding out of the box how their machine's going to survive, how it's going to last, how long it's going to run for, how often, and when they need to be doing the maintenance. And it's very, very controlled so that you just kind of get a better understanding of what you're going to get out of the machine. People are looking at what their cost of operating equipment is. I mean, this is something that we see, very commonly with air cylinder operations, but we're also seeing it in hydraulic systems. You've got a pretty sizable delta in efficiency between electrics and hydraulics. And I know there's, servo motors running power units, and they are making some new advancements in hydraulics to improve that efficiency, but you still do have a pretty sizable delta between electric and hydraulic there. And in a general sense, the power is only used when you need it. A lot of times you're going to have a big power unit that the motor's just always running, the pump's always generally under pressure, so you can have the power when the cylinder needs to move. But with motion control, the vast majority of your power only comes on when the actuator is moving. And so that certainly helps with your power consumption on multi-axis systems. Kind of touched on this a little bit on the reliability piece, but certainly the risk mitigation. You see some of the images here with a pretty dirty hydraulic cylinder. That's not terribly uncommon. I know in my own personal experiences, I've been the gentleman in the upper right cleaning up big pools of oil that have spilled out of a hydraulic system. And so, when you do have leaks, you don't have part contamination, and I know that's becoming more important in like the medical plastics industry, injection molding industries. Anytime a machine gets out of spec, you're not having to do rework costs, scrap rates, downtime as a function of that. And then also anytime somebody's walking by a machine that's run off of hydraulics, you've always got the risk of slips, spills. You've got the noise of the power unit again. So a lot of benefits from there with going down the path of electric, even in addition to the improved control you get with motion control, like we talk about with people wanting safe torque off, safe speed, safe position. All of those safety features are now getting built into motion control systems. Taking a step back and kind of comparing these benefits, we got a lot to talk about here, and I went through some of this kind of quick but you get rid of a lot of the part count, and you gain all of the benefits of motion control with precise position, speed, acceleration, really, really good force control, infinite flexibility, cut down on the component costs, cut down on the risk of contaminations, minimal maintenance, very, very quiet. And we're doing a lot more in like timber, security, oil and gas, general outdoor industry applications where even the hot and cold variation of temperature, which affects your oil and your overall performance, is now mitigated with using electric, because it self-compensates for the commands that you're asking it to do. Getting into applications, the red arrows are all pointing to Tolomatic actuators. And so we've had great successes in motion simulators. We've had good industry experience in the timber industries, and a lot with the metal forming, as you can see here. And as we talked about yesterday, metal tube bending. This, I believe, was the copper tube application that we talked about. We're doing a lot in the food industry where they've had to use hydraulics to do some of the high force, high speed applications, where now we're doing a lot of volumetric filling with electric actuators. And even with assembly and bearing presses here, you can see we've got a whole bunch of RSA actuators in this machine. So now that we've talked about what's good, what's not so good, where we've been successful, there's a lot of people that may have limited or no experience in dealing with hydraulics. And so I want to spend a little bit of time talking about some of the things that we've experienced and what we've come up with as good tips to help size electric actuators from an existing hydraulic application. And the biggest thing to remember is that when you're taking a look at hydraulic systems, it's not as simple as just taking your area times your pressure of the hydraulic system. That's oftentimes going to oversize your actuator, and it's going to lead to a very costly solution. And I'll talk about that in a few slides later. But what you want to do is really measure the exact forces. And we know that that's sometimes pretty challenging to do, especially in an existing machine. Sometimes you're not able to get to the port. Sometimes you're not able to use like a load cell, which would be ideal. But we do want to go down the path of getting some pressure readings, because that really is what tells us what the force is within a reasonable range. We can expect to see results in using pressure gauges on a hydraulic circuit to be within about 15% of the actual force, which really, by and large, if you're looking on the high end by about 10 or 15%, that gives you kind of a nice safety factor too. So the method to do this, it's not nearly as complicated as you would think. What you want to do is get a couple of gauges If you can get a load cell in there, great. If you can get them to buy a prototype, or if you can get an actuator into the machine and measure it electrically, that's even great too. So the best location, obviously, is if you can get right to the point of work on the cylinder. If you can get right on the work ports, awesome. If not, the closer you can get, the better. If that's on the valve, if there's on test ports, if there's some sort of unions or Y fittings or something like that you can get into, fantastic. And you want to make sure that you're measuring both sides of the circuit. We'll talk about why as we move on through this presentation. And the other thing you want to do is you want to operate the cylinder in both directions. You want to understand what your force is in extend and in retract, because every process might be a little bit different. And depending on what you're able to do, maybe you're just going to measure one port at a time. You're probably going to see a little bit of pressure bounce. You want to make sure that you're documenting this stuff great, and try to follow some kind of a sequence just so that you're keeping track of all of your different pressure measurements. I kind of put here as like designate a port A and do extend, retract, move your gauge, do your extend and retract, just something like that. So you're making sure that you're keeping your pressures correct on both. So like I talked about, the closer you can get to the point of work is great. This is probably going to be the most practical and accessible, is right where the hydraulic lines are going to go into and out of the valve. So we would call that probably a pretty good place. You don't want to measure back by the pump or something like that. Better yet would be somewhere midstream, whether that's like a flow control or flow dividers or something like that. That's another good spot to get closer to the point of work. And clearly, the best place would be if you can get your gauges right there on the cylinder itself. And that's probably one of the hardest places, depending on how it's installed. So I'm going to run through a little bit of an example here to show you all what this looks like. So hopefully the video's coming through here for everybody. I know with limited bandwidth, sometimes videos don't work the best, but what you can see here is we've got a little hydraulic simulator that we built here at Tolomatic, where we've got our extend pressure, which is the gauge on the right, going up to 450. And then we applied a little bit of back pressure on the return line, which was the gauge on the left there, which went to about 125 pounds. So we're going to work off of those pressures and this set of pressures in this circuit for the next few examples. So I talked about at the beginning, doing the area times pressure based off of your system ratings is not a great idea. And so we're going to talk a little bit about that here. So in the circuit that's on the screen, the system pressure was 1500 PSI. That's just kind of what we designed it to. And these cylinders are 1.5" bore with a 3/4 inch rod. When you do the math of 1500 times 1.5", the area times pressure here, you can see the math works out to that's about 2,650 pounds of available force. Okay, that's a pretty good amount of force you can get out of a little tiny cylinder on a little homemade stand that we built here. Another way to do this that people often think about doing is, well, I can just take my 400 PSI there on the left, which I show here, a little bit different orientation than the gauges. And I've got here, about 130 PSI on the return side or the downstream side. And so why couldn't I just take 400 minus 130 and then multiply that times the area, because that's the effective force or pressure being applied to the piston. It's certainly more accurate than doing area times pressure. And we'll show you here that now you see we've gone from 2,600 pounds of force down to about 270 pounds of force. So you can see it's getting a lot better, but it's still not as accurate as you could be. And a lot of times you might get lucky on this and it'll be okay, but we always want to be as accurate as we can, so we don't get into kind of a gotcha situation that could be a pretty painful experience for everybody. So again, this wouldn't be kind completely recommended, but it's getting us closer. The next way is really what we consider the most accurate. And so now you're going to be measuring both sides of your cylinder pressure, which we did in the other one, in the pressure differential, I'll call it. And I'm going to call this kind of a dual force, because we're going to take into account now the rod diameter as well, which, especially when you've got an 1.5-inch bore with a 3/4-inch rod, that's a pretty significant reduction in effective area on the rod end of the piston, right? And so that's where this becomes the most accurate, because you're taking into account what the true reactive force is on the rod side relevant to the blind side, or vice versa if your load is in retract. So we'll show you two different scenarios. The first one here is when you've got a high back pressure, and then we'll show you another one where there would be even lower back pressure than that 132 psi. And this type of thing would be where you have a high back pressure on the return end, would be more common in applications where it'd be like a servo hydraulic system or something like that. If it's normally just like a normal open center load sense system or something like that, you're probably going to usually have a pretty low return line pressure. But again, you don't know what you're getting into when you walk into a machine and start wanting to figure out what your pressures are. So in this instance, when we get rid of the effective rod diameter on your pressure, you can see now, had we just gone with the pressure differential method, we'd have been undersized by a few hundred pounds. And that may or may not make a difference. But again, with, it's not as simple as, well, I'll just buy another hydraulic cylinder that's an inch diameter bigger or smaller. This is a little bit different system, right? And so for this one, it's 539 pounds. So now we're going to go to a low back pressure. All right. So now we'll assume, you've only got maybe a couple of PSI or something like that. And so in the pressure differential here, you see now we're at 704 pounds of force. So again, the pressure has changed. The force has changed yet again. And then when we do the dual force, it's pretty much the same. So that's where the pressure differential method that I talk about, in a lot of hydraulic circuits, it's going to get you there, right? But you can see when you've got a high back pressure on your return line, it does make a difference in what your actual force is going to be. So like I say, in a lot of cases, you could probably get pretty lucky, but in some cases, it could come back to haunt you. And so let's take a look at what the different scenarios would have generated as far as an actuator, right? So if we would have done the system pressure, that would have driven the requirement for about a $3,600 actuator to get us a 2,600 pound force capacity. If we would have done the pressure differential using a high back pressure scenario, we would have thought we only needed a couple of pounds of force. Well, that would have been like a $450 actuator. So about almost a 10x difference between the two. And then by doing it the right way, you see that you're kind of right sizing it. You're not too hot, you're not too cold, you're just right. And so that's why it's really important not to, if nothing else, do the system pressure one, because you can see you wind up paying quite a bit more for your actuator. And when you get up into 5-ton, 10-ton, 20-ton type applications, this skew is going to be even more pronounced. We've got a nice little spreadsheet that we've put together so that you can actually go in and you can input these. Oh, I apologize. It's not letting me get in. Apologize. But we got a nice little spreadsheet on this, and you can contact your regional sales manager or any one of our Tolomatic apps engineers to get your hands on this spreadsheet. And I think we're even going to try and get this sent out to everybody through some kind of a link where we're going to post it online. So this is something that we've put together where you can just put in your bore diameters, your rod diameters, and just even track your application with your stroke length and your extend and retract times, which is going to help us with sizing up an application. And then you can also put in your working pressure and your back pressure in both your extend and retract, and we'll give you those force calculations automatically. So we've even kind of made a little tool to make doing the math a little bit more convenient. So hopefully this was helpful. Some other things to consider as far as converting hydraulics to electric is envelope and mounting is always going to be a challenge here, because you've got some power density differences between the two. So you may need a little more space with an electric actuator. Oftentimes you're going to. Very rarely, if ever, you're going to find something that's just going to drop in place. So there's going to have to be some sort of concessions made one way or the other to make sure that you can get an actuator in there. We're not able to do all the hydraulic applications in the world, right? So there's a lot of high forces happening in a lot of tight spaces, and so something might look like we can do it, and then once you get into it, we may not have the force because of the pressure and the cylinder sizes. We can do some pretty good strokes, but there's a lot of telescoping hydraulic cylinders. There's a lot of big cylinders out there that we may not be able to get to, but we're certainly trying to get some longer available stroke lengths in some of our RSX products for you. And you start running into some critical speed issues that you can bypass with big hydraulic lines and big accumulators that we may not be able to hit to. So just again, fully documenting and understanding the applications are pretty good. We're looking at a lot of mobile applications, and oftentimes these are able to run on like 24 and 48 volt options. That's a little tough to do with servo. You could probably get up to the 4,000 pound range on a low voltage setup, but you start losing speed, right? And so you got to be careful of what our capabilities are, or what the capabilities are of low voltage motors for these types of applications. And you also want to take a look at like what the shock loads are, especially when these things are going to be moving down the road, or you're going to be trying to drill holes in the ground with big augers or something like that. Shock loading can certainly provide challenges, and we want to be aware of those on the front end. And so, you know, there are some other higher performance options out there, but it's not very common. And also too, for two position applications, it's going to be probably pretty tough to justify an electric axis in a A to B, B to A type of an application. You know, it's pretty tough to justify that expense unless there's, you know, some significant pain or challenges with that existing application where electric just really truly brings a value to that process that hydraulic just can't deliver. So just a couple of things to consider there. When you're going to go out and try to understand what the forces are, again, just some things to think about here is you want to make sure that you're measuring, you know, kind of your inlet pressure if you're at the valve, and the return. It's kind of a worst case scenario, but again, it's going to give you something that's going to help minimize the risk of oversizing. So, you know, at least try to get 2 gauges on there and measure your forces, right? Again, I mentioned at the front end, if you can get a load cell in between the hydraulic cylinder and the point of work, that's ideal, that's best. That's going to give you a really good understanding of what the work is. Another option would be get some kind of a prototype assembly in there that would fit, and you can measure the current drive, the drive current, sorry. And that will further get you a little bit closer than measuring off of some gauges using a video and a phone. And then too, if you know, we've got a few guys for Tolomatic that have some little kits, and you can buy them online that have different little nipples and hoses and pressure transducers or gauges to measure. And if you have a kit that you keep with you, as you go from installation to installation, machine to machine, you want to make sure that you're kind of keeping track of the oils that are being used. Sometimes you may have a specialty oil in one machine and a standard oil in the other, and we don't want to cross-contaminate oil from one machine to the next and potentially cause component damage because of incompatible oils. So just something to kind of keep aware of and think about too. The best part is You don't have to be an expert, right? You know, we've got a lot of experience. We've been doing a lot of hydraulic conversions for a pretty long time now, and we've got a lot of tools. We've got a lot of people. We've got a lot of experience, so that you don't have to go it alone with understanding where to start or what you need to do. We're here to help. We've got lots of tools. We've got our sizing software. We've got our apps engineers. We've got our regional guys. We've got application worksheets. So certainly use Tolomatic as a resource to help understand what the requirements are and what might be the best electric alternatives to a hydraulic cylinder. And you know, we kind of want to be an education resource leader for everybody. So we've got these hydraulic pillar pages. We've got roller screw pillar pages, lots of educational resources. If you go to tolomatic.com, you can see I circled the info center. And as soon as you go to the info center, we've got a dedicated converting hydraulics to electric landing page. So we've got you know, how-to guides. We've got videos on how to measure and how to convert. We've got white papers on total cost of ownership and converting products over. So certainly use our website as a additional resource outside of our people and our experiences to find alternatives in the right application.